Right, so given an economic model of the firm, that is, we have to maximize the summation of beta times t, utility function of consumption in period 1 plus the utility function in this blah blah blah. Now just go through it. So for us to solve this question, remember we are asked to derive, this is where the question is, derive the Euler, that's the intertemporal Euler equation for consumption. So we can use the Lagrangian method or we can use the Bellman method. So I'm going to solve with the Lagrangian first and then the Bellman in another video. So the problem that is given, we are asked to maximize the summation. Sorry, this was misstated, so let me rewrite it correct. Then plus of UC1, so subject to CO plus K plus K1 equal to F of K0 plus 1 minus theta of K0, K1 equal to F of K1 plus 1 minus theta of K1. So if you want to understand the terms here, you can review your solo model and then you understand what each term means here. So this is our initial consumption in period 1 and this is our consumption in period 2. So this is consumption in period 1, capital in the next period, capital in the current period. What is left of capital in this period which we invest for the next period? So 1 minus delta here is where delta is the depreciation rate. Then capital next consumption next period depend on the capital from this year which was invested, and then the part of that capital which will be eaten up in the next period. So we are asked to derive an Euler equation in terms of consumption. So I'm going to use the Lagrangian method. If you want to see how we can solve this using Bellman method, you can watch the second video as well. So remember, I don't know if you're familiar with this, but when you're solving Lagrangian, it is you form an Lagrangian function by writing your objective equation subject to the constraint. Now we are going to introduce our multiplier, that's the Lagrangian multiplier. Sorry, I skipped some steps so you can watch that. Our multiplier. So I normally say that if you want to understand what this means, this is use of resources and this is the total resource we have. So which comes is the total use resource minus what you are going to use out of it. So this is going to be F of K naught plus minus 1 over this. Then for the first constraint, consumption in that period minus the capital. But since we have two constraints, we are going to have another multiplier. And here too, this is what we are going to use. This is the total, so it counts first. So F of K1 plus 1 minus what is left out of that, then minus what we use that for, which is C1. So that is the first step in solving Lagrangian. You specify your Lagrangian model, which is the function you have to maximize or minimize subject to the utility, that's the constraint functions given. So when you specify this, the next step is to take your first order condition. And when we talk about first order condition, it simply means taking partial derivative of all the variables. But before you start taking all the partial derivatives, I would like you to understand what are your decision variables in this case. What are the variables that we use in making analysis at the end of that? So we look at consumption in period 1, we look at consumption in the next period, and we look at capital in the next period. So these are the decision variables, and the decision variables are what you will use in taking your derivative. So we are going to first of all differentiate partially the Lagrangian function with respect to capital in the with respect to consumption in the first period. Now, since this is not explicitly defined, we are only going to say that whatever function that is here, we are going to take its derivative. If this was given in clear terms, we would have taken the derivative. Now, coming to this side, you see that there's no CO, so this is assumed to be a constant. Now, if you come here, there's no CO, but there's a CO here. Now, when you differentiate minus, remember there's a multiplier outside, minus multiply lambda 1 C1. When you differentiate this, since there is no power up there, this is going to be 1 times lambda. It will give me minus lambda minus 1. This will turn to 0, so the whole of this will disappear. So I'll bring down minus lambda. But remember, when you are taking first order conditions, you set it equal to 0. So this is my first equation. Again, we'll take it with respect to the second decision variable, which is C1. So if you come back to this place, there is no C1 here, but there is C1 here. But remember, there is a discount factor out there, which must be taken into consideration. So we have our that. I know it is power to t, but remember we are talking about period 1 and period 2. So at this point, t is equal to 1, and any number raised to the power of 1 is equal to that. So this end gives us t. Now, since this term is also not defined in clear terms, we're only going to take the derivative of that function. So if we run through all the other parts, you'll see that there's no C1 here, no C1 here, no C1, no C1, but we have C1 here. So the same way, if we multiply this by lambda outside and take the derivative of this, we are going to be left with minus lambda. So this is minus lambda 2, setting it into 0. This will give us 2. Now the last variable decision variable is k1. So here we are going to differentiate the function with respect to k1. There's no k1 here, 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 but you can see there's k1 here, which gives us minus 1k. But remember, there's a lambda out here, so this is. So again, if we differentiate this that is raised to the power of 1, we'll be left with just minus lambda 1. Now let's continue with the exploit. So let's check for k1 here. I hope you can see there's k1 here. But since this function is not clearly defined, it means we are going to hold on. Remember, we are differentiating this, and there's a k1 here, and there's what? No k1 here, right? So we are going to have plus. Remember, there's lambda out here, so this is going to be plus lambda 2 into this function is not clearly defined, so it's going to be f prime of k1 plus. So in this case, you can see that k1 is raised to the power of 1, so it will disappear. We have 1 minus delta. This is c1, so it will be left alone, and this is equal to 0. So this is our equation 2. So please watch the next video and see how I'll solve to the end. I don't want this to extend this minute.